Hey everyone, and welcome back to Talk Tensors. You know we love to dig into the latest and greatest in machine learning research, and today is no exception. We've got a real humdinger on our hands.
It's definitely one of those papers that makes you sit up and take notice. The kind that makes you think, okay, this could change things.
You're not kidding. Accelerating high-quality diffusion models with inner-loop feedback. That's the title, folks. Ambitious, right?
Yeah.
But also kind of intriguing.
Yeah, it gets right to the heart of a problem that's been bugging researchers for a while. How do we make these awesome diffusion models, which make those amazing images, run faster?
Right, because as it stands, they're great, but a bit slow.
Mhm.
Like if you need an image in a hurry, you might be waiting a while.
Especially if you want that really high quality photorealistic stuff, it can be a real bottleneck.
So this paper claims to have a solution, and a pretty clever one at that. This team from, get this, the University of Maryland aided NVIDIA, so you know there's some serious brain power behind this.
Smart folks, for sure. And they claim they've found a way to speed these models up, like significantly, without losing much, if any, image quality. That's the holy grail, right?
Absolutely. So before we get too deep into the weeds, let's do a quick level set for anyone who's maybe not familiar with diffusion models. Imagine taking a photo and turning it into pure noise, step by step.
Like dissolving it into static, basically.
Yeah, exactly. And then you teach a computer to reverse that process, to go from the noise back to the photo. That, in a nutshell, is a diffusion model. Pretty neat, huh?
It's surprisingly effective. Like, these things can create some seriously impressive images, especially when you consider they start with just random pixels.
But the problem is, as we said, they're slow. So that's where this paper comes in with its inner loop feedback, or ILF for short.
Right, that's their secret sauce. And it's all about making the image generation process smarter, not just brute forcing it faster.
Okay, I'm all for smarter, not harder. But how does it actually work?
It's kind of like giving the model a sneak peek at the final image as it's working.
Like a cheat sheet.
Kind of. It helps it make better decisions at each step so it doesn't waste time going down the wrong path.
Interesting. So it's less trial and error, more guided creation.
Exactly. More efficient and ultimately faster results. But before we jump into all the nitty-gritty details of ILF, I think it's worth taking a step back and looking at how we got here.
Yeah, good point. Diffusion models haven't always been the go-to for image generation, have they?
Not really. Remember GANs? Generative Adversarial Networks?
Oh, yeah. Those were the hot thing for a while.
Mhm.
But they were kind of notoriously tricky to work with, weren't they?
Definitely had their quirks. They could be tough to train, and sometimes the images they produced were, well, let's just say they weren't always the most realistic.
I've seen some of those early Jan creations. They had a certain abstract quality to them.
Yeah, that's one way to put it. But then along came diffusion models, and they were like a breath of fresh air. They were more stable, easier to train, and consistently produced much better results.
It was kind of a revolution in the field, wasn't it? Suddenly, you could create all sorts of incredible images that were almost indistinguishable from real photographs.
Yeah, it was a big deal. And they were also much more adaptable. You could use them for all sorts of different tasks, like generating images from text prompts, which is a huge breakthrough.
But as with any new technology, there were limitations. And one of the biggest ones, especially for those high-resolution, high-fidelity images, was speed.
Yeah, that was the trade-off. You could get amazing quality, but you had to be patient. Sometimes really patient.
So naturally, researchers started looking for ways to speed things up, right?
They did. And there were a couple of main approaches that emerged. One was called caching, which is basically reusing parts of previous calculations to save time.
Kind of like recycling, but for computations.
Oh, exactly. A clever idea, but it had its drawbacks. Sometimes the images would come out a bit blurry or lacking in detail.
Like a slightly out-of-focus photo, not ideal.
Right. And then there was distillation, which was all about training a smaller, faster model based on the knowledge of a bigger, slower one.
Like creating a cheat sheet, but for an AI model.
Exactly. It was like taking a huge textbook and condensing it into a handy study guide. But again, there were trade-offs.
I'm sensing a pattern here.
Yeah, the smaller distilled models often sacrifice some of the quality and detail of the original.
So it seems like ILF is doing something fundamentally different, wouldn't you say?
Absolutely. It's not about shrinking the model or reusing old calculations. It's about making the model itself smarter and more efficient at each step of the process.
Okay, now we're talking. So how does it actually work? Give us the inside scoop.
Well, imagine an artist sketching a portrait. They start with light, loose strokes to get the basic shapes and proportions down, right?
Yeah, I can picture that.
Well, ILF is kind of like giving the artist a glimpse of the finished portrait while they're still sketching.
Whoa, like a time-traveling art critic.
Huh, in a way. It allows the model to see where it's headed and make adjustments early on, resulting in a more refined and accurate final image.
So it's like the model is constantly getting feedback and course-correcting itself along the way.
Precisely. And that makes the whole process more efficient, leading to faster results without sacrificing quality. In fact, in some cases, ILF can even improve image quality compared to traditional diffusion models.
Now, that's impressive. So it's not just about speed, it's about getting better results overall.
Exactly. And that's what makes ILF so exciting. It has the potential to unlock a whole new world of applications for diffusion models.
Okay, I'm definitely hooked. But before we get too carried away with the possibilities, let's break down how ILF actually works on a technical level.
Sounds good. There are three key components: learnable feedback rescaling, fast approximate distillation, and feedback-aware inference scheduling.
Okay, those are some serious technical terms. Can you unpack those a little bit for us mere mortals?
Sure. So learnable feedback rescaling is all about making sure the feedback the model gets doesn't overwhelm it.
Because too much feedback could be a bad thing.
Exactly. Imagine trying to learn something new, but someone's constantly shouting corrections at you. It would be hard to focus, right?
Yeah, I'd probably just shut down.
Exactly. So learnable feedback rescaling is like a volume knob for that feedback. It lets the model adjust how much it listens to the feedback so it's helpful, not overwhelming.
Makes sense. So what about fast approximate distillation? What's that all about?
Well, this one is all about efficiency. Remember how we talked about distillation earlier, training a smaller model based on a bigger one?
Yeah, the condensed textbook approach.
Right. Fast approximate distillation is a way to do that even more efficiently. It's like giving the feedback module a super condensed version of the textbook so it learns even faster.
Clever.
Yeah.
And finally, we have feedback-aware inference scheduling. What's that one do?
This one's all about timing. It figures out when is the best time to give the model feedback during the image generation process.
So it's not just about what feedback to give, but when to give it.
Exactly. They found that applying feedback at certain stages is more effective than others. Like early on, when the model is just starting to sketch out the image, and then again later on when it's refining the details.
So it's like a chef adding seasoning at just the right moments to bring out the best flavors in a dish.
That's a great analogy. It's all about timing and precision.
This is all starting to come together. But before we move on, I want to make sure I understand something. You mentioned that ILF can actually improve image quality in some cases. How is that possible?
Well, sometimes traditional diffusion models can get stuck in a rut. They might produce an image that's technically correct, but lacks a certain level of realism or detail.
Like it's missing that certain spark.
Exactly. And that's where ILF comes in. The feedback helps nudge the model out of that rut so it can explore new possibilities and create even more impressive images.
Okay, now that's really cool. So we're talking about not just faster image generation, but potentially even better images?
Precisely. And that's what makes this research so groundbreaking. It's pushing the boundaries of what we thought was possible with diffusion models.
All right, so we've talked a lot about how ILF works, but the real question is, does it actually deliver? Does it live up to the hype?
Well, that's what the researchers set out to test. And based on the results in the paper, it seems like they're onto something pretty special.
Okay, I'm all ears. Give us the highlights.
All right, so they tested ILF on a few different types of diffusion models. One type they focused on was diffusion transformers, or DITs for short.
DITs. Those sound familiar. Don't they have something to do with those big language models everyone's talking about? Like ChatGPT?
You got it. Transformers have been a game changer in natural language processing, and now they're making waves in image generation too. And DITs in particular are really good at creating high-resolution images.
So they're perfect for putting ILF to the test.
Exactly. And the results, well, they were pretty impressive. They saw speedups of 1.7x to 1.8x compared to the baseline models.
Wait, so they were able to generate images almost twice as fast?
Yep, that's right.
Wow, that's a significant improvement. Imagine the time you could save if you're a designer or an architect or anyone working with complex visuals.
Absolutely. And here's the kicker. They didn't have to sacrifice image quality to get those speedups. In fact, in some cases, the images generated with ILF were actually better than the ones produced by the original models.
Hold on, really? How is that even possible?
It seems like that feedback loop in ILF helps the model avoid getting stuck in certain patterns. Like sometimes diffusion models can get into a creative rut,
Yeah, I can see that.
And ILF helps break them out of that rut so they can explore new possibilities and create even more unique and impressive images.
That's fascinating. So it's not just about speed, it's about unlocking even more creativity from these models.
Exactly. But they didn't stop there. They also tested ILF on another popular model, Stable Diffusion, which is widely used for text-to-image generation.
Oh yeah, stable diffusion. That's the one that lets you type in a description and it creates an image based on that, right?
That's the one. And guess what? They saw similar results. Significant speedups without any noticeable drop in quality.
So it seems like ILF is a pretty versatile technique. It can be applied to different types of diffusion models and still deliver the goods.
That's right. And that's one of the things that makes this research so exciting. It has the potential to impact a wide range of applications.
Speaking of applications, I'd love to hear your thoughts on how ILF could be used in the real world. Like what kind of impact could this have on different industries?
Well, the most obvious application is in AI art and content creation. Imagine being able to generate high-quality images and videos in real time.
No more waiting hours for things to render.
Exactly. That would be huge for video game developers, filmmakers, even social media companies.
It would totally change the way we create and consume media.
Absolutely. And beyond entertainment, ILF could also have a major impact on fields like design, architecture, and engineering.
Yeah, those are all fields where speed and visual fidelity are critical.
Right. Imagine being able to rapidly prototype and test different designs or create realistic simulations in a fraction of the time it takes now.
It would be a game changer for innovation. We could explore so many more possibilities.
Exactly. And let's not forget about scientific research. ILF could be used to speed up the analysis of large data sets or create complex simulations for things like climate modeling or drug discovery.
Wow, it really seems like the possibilities are endless. But I know we have to be careful about getting too carried away with the hype. Are there any limitations or challenges associated with ILF that we should be aware of?
Of course, every new technology has its limitations. One thing to keep in mind is that ILF still relies on pre-trained diffusion models. So the quality of the images it generates will always depend on the quality of the underlying model.
So if the original model has biases or limitations, ILF won't magically fix those.
Right. It's not a silver bullet. And another challenge is that training the feedback module in ILF can still be pretty computationally expensive.
So there's still room for improvement in terms of efficiency.
Definitely. But even with those limitations, I think ILF is a huge step forward. It's a really clever approach to a problem that's been holding back the field for a while.
I agree, it's an exciting development. But before we move on to our novel notions segment, I want to circle back to those three key components of ILF. I think it would be helpful to dig a little deeper into how they actually work together.
Sure, happy to break it down further. Let's start with learnable feedback rescaling. Remember, that's the one that's like a volume knob for the feedback.
Right. Can you explain how that works in practice?
So the feedback module is essentially sending information back to the main diffusion model, telling it, hey, you're on the right track, or maybe try something different here.
Like a little voice whispering in its ear.
Kind of, but if that voice is too loud, it can drown out the model's own learning process.
Ah, so that's where the rescaling comes in.
Exactly. It's like adjusting the volume so the feedback is helpful, not overwhelming. And the cool thing is the model actually learns how to do this rescaling itself during the training process.
So it figures out how much feedback it needs to listen to. That's pretty smart.
It is. It's like a student learning how to best take advice from their teacher.
Love that analogy. Okay, what about fast approximate distillation? How does that speed up the training process?
So remember how we talked about using a smaller, simplified model to train the feedback module? Well, fast approximate distillation takes that to another level. It finds an even more efficient way to do that simplification.
So it's like creating a Cliff's Notes version of the Cliff's Notes.
Exactly. It's all about finding shortcuts without sacrificing too much accuracy.
Genius. And last but not least, we have feedback-aware inference scheduling.
This one is all about timing. Remember, the model gets feedback at different stages of the image generation process. Well, feedback-aware inference scheduling figures out the optimal times to give that feedback.
So it's not just about what to say, but when to say it.
You got it. And what they found is that giving feedback early on, when the model is just starting to form the image, is really important. And then giving feedback again later on, when it's refining the details, is also helpful. But giving feedback in the middle stages doesn't seem to make as much of a difference.
Interesting. So it's all about finding those key moments where the feedback will have the biggest impact.
Exactly. It's like knowing when to offer encouragement and when to step back and let the model do its thing.
This has been really insightful. I'm really starting to appreciate the level of thought and ingenuity that went into designing ILF.
It's definitely a testament to the creativity of the researchers. They've come up with a really elegant solution to a tough problem.
Well said. And now, for the moment you've all been waiting for, it's time for Novel Notions.
The part of the show where we let our imaginations run wild and explore the what ifs and the could we.
Exactly. So let's dive in, shall we? I've been thinking about the potential of ILF beyond just image generation, and I have an idea that might sound a bit out there.
Hit me with it.
What if we could apply ILF to something like personalized medicine?
Personalized medicine. How so?
Well, imagine if we could use diffusion models enhanced by ILF to create highly accurate patient-specific models of diseases. Like, imagine being able to simulate the progression of a disease in a virtual environment.
So instead of just looking at static data, we could actually see how a disease might evolve over time in a specific patient.
Exactly. And then we could use those simulations to test different treatment options and see which ones might be most effective for that individual patient.
That would be incredible. It would be like having a virtual lab where you could experiment with different treatments before actually administering them to a patient.
Exactly. And with ILF speeding up the simulation process, doctors could make faster, more informed decisions about the best course of treatment.
It would revolutionize healthcare. We could potentially develop personalized treatments that are tailored to each patient's unique needs.
And who knows, maybe we can even use these simulations to develop entirely new treatments that we hadn't even thought of before.
It's an exciting thought. But of course, there would be a lot of challenges to overcome. We'd need massive amounts of data, and we'd need to make sure these models are accurate and reliable.
Absolutely. And there are definitely ethical considerations to think about as well. But I think the potential benefits are so great that it's worth exploring.
I agree. It's a testament to the power of this technology that we can even have these kinds of conversations. Who knows what the future holds? It really makes you wonder what other breakthroughs are just around the corner, you know?
It does. It feels like we're on the verge of some really incredible things. But before we get too lost in the future, I want to bring us back to something you mentioned earlier, that idea of using ILF to accelerate the evolution of AI itself.
Oh, right. That was a fun thought experiment.
Yeah,
Using diffusion models to create synthetic data that's specifically designed to help AI learn faster.
Exactly. Like, what if instead of training AI on real-world data, which can be messy and unpredictable, we could give it this perfectly curated synthetic data that's tailored to its specific needs?
It would be like creating a personalized curriculum for an AI, wouldn't it? A set of lessons designed to help it learn and grow as efficiently as possible.
Exactly. And because ILF makes the data generation process so much faster, we could potentially accelerate the rate at which AI learns and evolves.
It's like giving AI a turbo boost. We could see entirely new AI architectures emerge, ones that are more efficient, more powerful, and more capable than anything we have today.
It's mind-blowing to think about the possibilities. We might even discover entirely new forms of intelligence that we can't even imagine right now.
It's a bit like opening Pandora's box, isn't it? We're stepping into uncharted territory.
It is a little daunting, but mostly I think it's incredibly exciting. This research is a reminder that we're constantly pushing the boundaries of what's possible.
Absolutely. And who knows what amazing discoveries await us just around the bend.
Well, on that note of boundless possibility, I think it's time to wrap up this deep dive.
Sounds good to me.
It's been a fascinating journey exploring the world of ILF and diffusion models, from speeding up image generation to potentially revolutionizing fields like medicine and even AI itself. It's clear that this technology has the power to reshape our world in profound ways.
I couldn't agree more. It's an exciting time to be working in this field, that's for sure.
Before we sign off, I want to remind everyone to check out the show notes for links to the full paper and other resources where you can learn more about ILF and diffusion models.
And if you have any novel notions of your own that you'd like to share, we'd love to hear them. You can find us on all the usual social media platforms.
And until next time, keep exploring, keep learning, and keep those imaginations firing.
And keep diving deep.